In this video, we'll discuss Faraday's law and Lenz's law, and specifically how a changing external B field relates to Faraday's law. And then in the next two videos, we'll continue with Faraday's law and Lenz's law with a couple of other applications. So in the last module, we said that a changing magnetic flux in a coil or loop induces an EMF in that coil or loop, and that this is called electromagnetic induction. So this is a different mechanism to generate an EMF than we saw with a battery. With a battery, we generate an EMF with the chemical reactions inside the battery. But this mechanism generates an EMF with mechanical motion. It's the mechanism that a typical generator uses. It's also the principle that will help us understand how a transformer works when we get to that topic. Mathematically, the statement I just wrote can be written this way. And this equation is called Faraday's law. And let me identify all the variables in this equation. So the first variable is the induced EMF, and N is the number of turns in the coil, or if it's just a single loop, N would be 1. And delta phi B is the change in magnetic flux. And we learned what the magnetic flux was in the last module, so we can rewrite this change this way as the change in BA cosine theta. And then delta T is the change in time, or it's the time over which the flux is being changed. The negative sign in the equation relates the direction of the EMF to the change in flux. It can be tricky to get this right, so we'll just use Faraday's law to calculate the magnitude of the induced EMF. And then we'll get the direction of the induced EMF from Lenz's law. And we'll discuss Lenz's law in just a minute. Let's take a closer look at Faraday's law first. Substituting in the equation for flux, then we can write Faraday's law this way, which is very often how we'll apply the equation. By looking at the equation this way, we can see the three ways that were mentioned in the previous module to induce an EMF. An EMF is induced by changing the external B field, the area of the loop or coil, and the angle between the coil and the external B field. We'll deal with each of these one at a time, starting with the changing external B field method. So to help you visualize what we're talking about, let me draw this picture. So here's, say, a coil of wire, and then there's an external B field, which is not made by this coil. This coil right now doesn't have a current in it. It's not making a magnetic field at all. So here's an external B field that's made by something else, perhaps some bar magnets or some other wires with currents. And so initially, let's say this magnetic field is just constant, and there's no current in this coil either. But now if we change one of the variables in Faraday's law, either the external B field, or the area of this coil, or the angle of the coil with respect to the B field, then we will induce an EMF, and then a resulting current, in the coil. And so let's say we change this external B field, meaning it increases or decreases in magnitude, and then that will induce an EMF or a voltage in this coil, and then that EMF can push a current around this coil. And in class I'll do a demonstration showing that this actually happens. So when we do this, how do we know the direction of the induced EMF and therefore the direction of the current? So this is given to us by Lenz's law. So Lenz's law states that the induced EMF and current are in the direction that will induce a second magnetic field and associated flux that opposes the original change in flux. And to make use of this, we'll turn this into a procedure. So here's the procedure to apply Lenz's law. So the first thing you want to do is make a drawing with the coil or loop and show the direction of the external B field. Then add an induced B field according to the following rules. If the flux is increasing, then the induced B field inside the coil is in the same direction as the external B field. If the flux is decreasing, then the induced B field inside the coil is in the same direction as the external B field. Then use right-hand rule number 2 to find the direction of the current that would produce a B field in the direction of the induced B field. and then that is the direction of the induced EMF and the induced current if a current is permitted to flow, which we'll discuss in just a minute. Okay, so to try to make sense of this procedure, I'll go through an example, but then also there are 3 complete worked out examples in Moodle in the module 23B, and those examples apply Faraday's law and Lenz's law, and so you should take a look at those. So here's a basic example, though, applying this procedure for Lenz's law. So here's a coil, and then let's say there's an external B field, meaning a B field that's not made by this coil, it's made by something else, and the B field is going into the screen. And then the question we're given is, if the external B field decreases, what is the direction of the induced EMF in the coil? So we'll follow the procedure. Step 1 is to show the external B field, and that's already done for us. It goes into the page. And then step 2, if the external B field decreases, then that means the flux decreases. And that's because the flux is BA cosine theta. So if one of these variables, such as B external, decreases, then the flux decreases. Then Lenz's law says, if the flux decreases, we get an induced B field inside the coil in the same direction as the external B field. So now let's draw the induced B field inside the coil. And now the third step, we'll use right-hand rule number 2 to determine the direction of the induced current, which then gives us the direction of the induced EMF. So you might say we're using this rule backwards, where we're given the direction of the B field and we want to find the current instead of the other way around. So I think a simple way to do this is just to try the 2 directions of current and see which one works. If we assume the current is going in the counterclockwise direction like this, and if you apply the right-hand rule with that, then the B field inside the coil is coming out of the screen, and that's not the direction that we determined in step 2. So that direction of current doesn't work. So then we try the other way. And so now if you put your thumb in the direction of that current, you see that the B field inside the coil is going into the screen, and that matches with what we found in step 2. And so that's the correct direction of the current, and then the induced current and the induced EMF always go together. So that's also the direction of the induced EMF. And so the answer is it's going clockwise. So one more detail here. If this coil or loop did not form a complete closed circuit, then current would not be permitted to flow. We would still go through this entire process and come to the same conclusion that the induced current and induced EMF are going clockwise in this case. But since the current can't flow if the loop is not complete, then we still get the induced EMF, we just will not actually get a current to flow. Okay, so that's the end of this video on Faraday's law and Lenz's law, specifically dealing with a changing magnetic field. In the next 2 modules, we'll apply Faraday's law and Lenz's laws again to a changing area and changing angle.